Have you ever wondered about the mystery and fascination of supernovae, the spectacular celestial fireworks that light up the cosmos? These celestial phenomena are indeed a sight to behold. Supernovae are the awe-inspiring explosions that mark the end of life for massive stars. They are one of the most captivating and consequential events in the universe, shaping the cosmic landscape in ways that we're still striving to fully comprehend. These intense, stellar explosions hold a special place in the hearts of astronomy enthusiasts, sparking intrigue and a myriad of questions. But it's not just stargazers who are fascinated. Scientists, too, find themselves in the grip of these cosmic enigmas, their research continually unveiling new layers of understanding. The life cycle of a supernova, from its dramatic birth to its consequential death, is a journey filled with discovery and wonder. So, let's dive in, shall we? Join in as we explore the life cycle of a supernova, from its dramatic birth to its consequential death. The story of a supernova begins with the life of a star. This vibrant, fiery orb of gas, glowing in the velvet expanse of the cosmos, is an emblem of life's impermanence. Stars, like us, are born, they live, and they die. Their life cycle is a cosmic ballet choreographed by the fundamental forces of nature. In the heart of a star, a grand spectacle unfolds. Through a process known as nuclear fusion, lighter elements merge to form heavier ones, releasing colossal amounts of energy. This energy powers the star's glow and creates an outward pressure that counteracts the inward pull of gravity. It's a delicate balance, a cosmic dance between the forces of creation and destruction. However, as stars age, they exhaust their nuclear fuel. For smaller stars, this endgame results in a peaceful retirement as a white dwarf. But for the more massive stars, those 10 times or more the mass of our sun, the finale is far more dramatic. Once these behemoths deplete their nuclear fuel, there's nothing left to resist the immense gravitational pull. The core of the star collapses under its own weight, triggering a cascade of events leading to one of the most spectacular phenomena in the universe, a supernova. Not all supernovae are created equal. This statement rings true in the astonishingly diverse cosmos we inhabit. Supernovae, these dramatic celestial fireworks, come in a variety of types, each with its unique characteristics and implications. Broadly speaking, supernovae are classified into two main types, Type 1 and Type 2. Let's delve a little deeper to understand what sets them apart. Type 1 supernovae are intriguing. They don't show hydrogen lines in their spectra, which is a bit of a mystery given that hydrogen is the most abundant element in the universe. So where does the hydrogen go? Well, scientists believe that Type 1 supernovae are often associated with binary star systems. In these systems, a white dwarf star draws material from a companion star. When the white dwarf accretes enough matter and surpasses a critical mass, it triggers a thermonuclear explosion, resulting in a Type 1 supernova. The lack of hydrogen lines in their spectra might be because the white dwarf has already exhausted its hydrogen fuel before the explosion. On the other hand, we have Type 2 supernovae. These are the explosive deaths of massive hydrogen-rich stars. When such a star exhausts its nuclear fuel, it can no longer support its own weight. The core collapses under the immense force of gravity, and the outer layers of the star are blasted off in a spectacular explosion. The presence of hydrogen lines in the spectrum of Type 2 supernovae is a telltale sign of their origin from hydrogen-rich stars. So, Type 1 or Type 2? Which one is more powerful, you might wonder? Well, both types release an immense amount of energy, each in their unique way. The energy released is so staggering that it can outshine an entire galaxy for a brief period. In essence, these two types of supernovae are like cosmic detectives, offering us clues about the life cycles of different types of stars. Whether it's a white dwarf in a binary system or a solitary massive star, the type of a supernova offers clues about its progenitor star and the explosive mechanism behind it. The explosion of a supernova releases an unimaginable amount of energy. Think about a star, silently burning in the cosmos, suddenly detonating with the radiance of an entire galaxy. But what sparks such a cataclysmic event? Well, it's all about what happens deep within the star. For Type 2 supernovae, the story begins with a massive star running out of nuclear fuel. The star's core starts to collapse under its own gravity, and as it does, it creates an enormous shockwave. This shockwave, powered by the gravitational pressure overpowering nuclear forces, races through the star, ultimately ripping it apart in a dramatic display of stellar destruction. On the other hand, Type 1 supernovae have a slightly different narrative. These supernovae occur when a white dwarf, part of a binary system, accretes enough material from its companion star. Once it surpasses a critical mass, the white dwarf detonates in a colossal explosion. The violent deaths of these stars give birth to some of the most intense explosions in the universe. Supernovae serve as cosmic crucibles, forging new elements in their fiery furnaces. The intense heat and pressure generated during a supernova explosion provide the perfect conditions for nucleosynthesis, the process that creates new atomic nuclei from pre-existing ones. Nucleosynthesis in a supernova is a remarkable event. As the star explodes, its core collapses under the immense gravitational force, creating extraordinary temperatures and pressures. These conditions allow elements lighter than iron to fuse together, forming heavier elements, from iron all the way up to uranium. This fusion releases enormous amounts of energy, contributing to the supernova's brilliance. However, the ultimate contribution of a supernova extends far beyond its dramatic display. The explosion not only creates new elements but also propels them out into the cosmos at incredible speeds. This dispersal of elements, aptly termed stellar wind, carries these freshly forged elements across vast distances. Over time, these materials become part of interstellar clouds, the birthplaces of new stars and planets. The significance of this elemental dispersal is profound. Many of the elements essential for the formation of planets, and even life itself, are produced in supernova. The iron in our blood, the calcium in our bones, the oxygen we breathe, all these elements were once part of a star that ended its life in a spectacular explosion. Furthermore, the elements dispersed by supernovae enrich the interstellar medium, contributing to the chemical diversity of galaxies. This diversity is essential for the formation of planets with varied compositions, which in turn may support the existence of diverse life forms. In essence, supernovae are responsible for seeding the universe with the building blocks of planets and life. They are cosmic factories that churn out the raw materials necessary for the creation and sustenance of complex structures in the universe. The legacy of a supernova lives on in the elements it scatters across the cosmos. Every breath we take, every step we make, we owe it to the long-dead stars that exploded as supernovae. We truly are, in the most literal sense, stardust. The impacts of supernovae extend far beyond their explosive deaths. These majestic stellar phenomena have profound implications that resonate across the cosmos, shaping the very architecture and destiny of galaxies. One of the most fascinating roles of supernovae, specifically type Ia supernovae, is their function as cosmic distance indicators. This might seem peculiar at first, but let me explain. You see, the luminosity of these explosions is remarkably consistent. This means that by observing a supernova's brightness from our vantage point, astronomers can accurately calculate its distance from us. It's like knowing the wattage of a light bulb and using its perceived brightness to judge how far away it is. This ability to gauge cosmic distances has brought about groundbreaking revelations in our understanding of the universe. In fact, it was through studying type Ia supernovae that scientists discovered the universe is not just expanding, but accelerating in its expansion. This unexpected finding led to the conceptualization of what we now know as dark energy, a mysterious force driving the accelerating expansion of the universe. Not only do supernovae help us measure the universe, they also actively participate in shaping it. Supernovae explosions disperse heavy elements across galaxies, seeding the cosmos with the raw materials that give birth to new stars and planets. They stir up the interstellar medium, triggering the formation of new stars and influencing the dynamics of galaxies. It's not an exaggeration to say that without supernovae, the universe as we know it would be vastly different. These stellar explosions are vital players in the cosmic symphony, contributing to the ongoing evolution and transformation of the universe. Supernovae stand as cosmic beacons, illuminating the intricate processes governing the universe. Their explosive deaths give rise to new beginnings. Their radiance pierces the depths of cosmic mysteries, and their remnants echo the grand narrative of cosmic evolution. Indeed, in the realm of astronomy, supernova are not just spectacles of destruction, but harbingers of creation and change.